This is fundamental problem 16 from chapter 13. The 0.2 kilogram pin P is constrained to move in the smooth curved slot, which is defined by the lemniscate R is equal to 0.6 times cosine of 2 theta. Now, before you get too excited about this, we are going to be looking when the angle is equal to 0 degrees, so like this, at which point R would just be equal to 0.6. However, we are going to have to use this equation because we need to know what R dot and R double dot are. Its motion is controlled by the rotation of the slotted arm OA, which has a constant clockwise angular velocity of -3 radians per second, which means theta double dot is equal to 0. We want to determine the force arm OA exerts on pin P when theta is equal to 0 degrees. Motion is in the vertical plane, which means we have a force of gravity acting downwards like this. So I'm going to call the force that arm OA exerts on the pin P, I'm going to call that force F. And when the angle is equal to 0 degrees, that force, that has to be perpendicular or normal to the surface here. So that would be acting straight up. So we have our non-contact force, which is the force of gravity. We have the force that the arm exerts on the pin, which has to be perpendicular to the surface of contact. We also have, what do we want to call this? It's moving in the smooth curved slot, so the surface of the smooth curved slot is exerting a force on the pin also. That force has to be perpendicular to the surface as well. For both of these forces, the one that the arm exerts on the pin and the one that the smooth curved slot exerts on the pin, we could have a component which was parallel to the surface also, and that would be a frictional force, but it says here a smooth curved slot, so there'd be no friction because it's smooth. And for the force that the pin exerts on the arm, that is just going to have a upwards component. So we want to determine the radial direction and the transverse direction. We have the origin here, so the radial direction when the angle is equal to 0 is just pointing straight outward like this, and the transverse direction is perpendicular to that. We have, as we said, a force of gravity acting downwards, the force of the arm acting upwards, and the normal force that the smooth curved slot exerts on the pin. I said it's acting inwards, and we don't actually need to find this force, but if you said it's acting outwards, you would figure out by the sign that it was actually acting inwards, so that would be fine. If you don't know what direction it's acting in, as long as you know it's perpendicular to the surface of contact, you can figure out whether it's inwards or outwards by looking at the sign. Okay, so the angle is equal to 0 degrees when we're looking at this. Theta dot is equal to -3. Theta double dot is equal to 0. We have R equal to 0.6. When theta is equal to 0, we take a derivative with respect to time. The derivative of cosine is negative sine. I have to then use the chain rule and take the derivative of 2 theta, which is 2 times theta dot. So this becomes -1.2 times sine of 2 theta times theta dot. Evaluated when theta is equal to 0, that just gives me 0. Then for R double dot, I have to take another time derivative of this. I have to use the product rule along with the chain rule. So for the product rule, I have -1.2 times the derivative of sine of 2 theta with respect to t times theta dot. When I take a derivative of sine 2 theta with respect to t, I get cosine of 2 theta times 2 theta dot from using the chain rule. So that becomes -2.4 cosine of 2 theta. And then I had a theta dot here and another theta dot from the chain rule. So that's theta dot squared. And then I have to take the derivative of then I have -1.2 times sine of 2 theta times the derivative of theta dot with respect to t, which is just the -1.2 times sine of 2 theta times theta double dot. Evaluated when the angle is equal to 0 degrees, that gives me -21.6. Then I use, this is from the equation sheet, in the radial direction I sum up the forces. The radial component of the acceleration is r double dot minus r times theta dot squared, and the transverse component of the acceleration is r times theta double dot plus 2 times r dot times theta dot. So I'm going to figure out what the radial and the transverse components are by taking what I have here and plugging it in. So r double dot is equal to negative 21.6. R is equal to 0.6 when theta is equal to 0, and theta dot is equal to negative 3, so that gives me negative 27. In the transverse direction, I have theta double dot is equal to 0, but r dot is also equal to 0, so in the transverse direction, the acceleration is just equal to 0. This is the transverse direction. Summing up the forces in the transverse direction, I have F minus mg is equal to 0. Therefore, the force, which we're looking for, is just equal to m times g. So the force that arm OA exerts on pin P is 1.96 newtons. If you wanted to know the normal force that the smooth curved slot exerts on the pin, you could look at the forces in the radial direction. I said the normal force was acting inward, so that would be minus n is equal to the mass times the acceleration, which is negative 27. But if you just said that the normal force was acting outwards, then you'd have n is equal to negative 0.2 times 27. And since you have that negative sign there, it means the normal force is actually pointing in the opposite direction of what you said. And that concludes Fundamental Problem 16.